Okay, we're doing the second half of 4.1, and this time we're going to be dealing with angular speed and linear speed. In this section, you will calculate angular speed and linear speed. Linear speed is like you're running on a flat ground, or you're running a distance, whether you're turning or not, you're still running a linear measurement, such as miles or feet or meters. Okay, and you can either be running or moving in a car at 40 miles per hour. So you're still moving in a direction, whether you're turning or not. You're still moving in a distance where you can measure it by a linear measurement, like miles or feet. Angular speed, on the other hand, you're going to measure it by the angle. And angles are measured in degrees. And since yesterday, you now know that angles can be also be measured in radians. So you can have maybe like 6 degrees per minute. That's the speed of the minute hand on a clock. Okay. And you know that the second hand runs faster, so it has a faster angular speed, and the hour hand has a slower angular speed than the minute hand. Okay. Now, if you're running around the clock, that would be measured in maybe, let's say, inches, and that would be linear speed and not angular speed. Even though you're going around it, you're not measuring the degrees or the radians. You're measuring how far you've ran. Okay, so that would be 6 inches per second, or whatever it would be, because you're going around it. Because the bigger the clock, the farther you have to run. Whereas when we're talking about the angle, it doesn't matter how big the clock is. It could be a giant clock on a tower like Big Ben, or it could be your watch on your arm. This minute hand goes at the same speed, right? It makes the same angle per time. Alright, so that's how you're going to remember how the difference between angular speed and linear speed is that angular speed is measured by change the movement as an angle per time. That's what speed is, right? Speed is a certain change per time, and the linear speed is how long you've run. So on this one, angular speed, it doesn't matter how big the clock is, because you're measuring the angle only. And linear speed, it does matter how big the clock is, because you're running around it in a linear fashion, or measuring in linear measurements. Our first problem, angular speed and linear speed. A wheel has a diameter of 3 feet and rotates at 60 revolutions per minute. A revolution is one turn around. So this wheel is going to turn 60 times around every minute per minute, 60 revolutions per minute. Find the angular speed in radians per second. And then we're going to find the linear speed in feet per second. One is linear, okay, feet, and one is angular in radians. So what we're going to do is figure out what we know. We are given that the wheel turns at 60 revolutions per minute, and we have a diameter of 3 feet. Okay, and we're trying to find radians per second. So what we need to do is change the revolutions to radians. We also have to change the minutes to seconds. So here we go. First, we need some kind of conversion for revolutions to radians. And we know one revolution, one spin around, and the radians for one spin around, How many radians is one spin around? Well, that's 2 pi. We learned that yesterday. So 2 pi radians is the same thing as 1 revolution. And we can use this as a conversion because this is equal to 1. Alright, doing the problem, we start with 60 revolutions per minute. By the way, this technique that I'm using for this is called unit analysis, and it's very, very, very helpful when you're trying to solve a math problem that involves like a word problem that involves units, and where you have the units. You can do a lot of problems this way in science and math if you can keep track of the units. Let's see what I mean by that. So I'm going to convert revolutions to radians. So I can use this conversion factor of 2 pi radians to 1 revolution by multiplying that. We use it this way because we have the radians in the denominator and the numerator, and we can cancel those. If we wanted to cancel the radians, then we would take the reciprocal of this fraction and we can cancel the radians. But right now we want to cancel the radians, and we want to go from radians to, cancel the revolutions. We're trying to get the revolutions into radians, so not radians. I've done my job here for the first part. Now I have to change the minutes to seconds. What's our conversion for minutes to seconds? Well, we know that 1 minute is equal to 60 seconds. Where do we want to put the minutes? In the numerator or in the denominator if we want to cancel it with this minutes down here? Okay, we have to put it in the numerator so I can cancel it with the minutes in the denominator. So cancel those. Now all we have to do is finish the arithmetic, basically calculator work. But I don't trust my calculator that much, so if I see something easy that I can do here, I go ahead and do it, like canceling the 60s. The 60 in the numerator cancels with the 60 in the denominator. Now I'll have it all cleaned up, no more numbers to play with, so we just go ahead and write the answer as 2 pi radians per second. All the other things, numbers and units, have been reduced away, and that's my answer, 2 pi radians per second. Okay. Now we're going to do the second half, part B, where we're trying to find the linear speed. We're still given 60 revolutions per minute and the diameter is 3 feet. Now instead of needing 1 revolution is equal to 2 pi radians, we need some kind of conversion that will give me revolutions to feet. Now we know that 1 full circle, not in angles, but on the edge of this, is really the circumference. So we need the circumference relationship. So we know that the circumference is equal to the diameter times pi. If you wonder where this comes from the definition of pi. We know pi by taking the circumference, the outside measurement. If we took a tape measure and measure the outside of my circle, that's the circumference, and we divide it by the diameter, we're going to get 3.1417, etc. Okay, it goes on. If it's c divided by d is equal to pi, we can say that c is equal to d times pi. Okay. So we know that for this problem, the diameter is 3 feet, so we can put the 3 feet, 3 times pi, and that will give me 3 feet per revolution, 3 pi feet per revolution. Okay, now we're ready to go and do the